This presentation is delivered by the Stanford Center for Professional Development.
Hey there. All right, so thank you very much for your duty to the CS 106B midterm exam last night. An unusual event by all accounts, but we did all manage to get it done. And okay, we'll go on. I'll finish. This is the last slide that we had shown on Friday, and I had just blasted it up there and then didn't really talk about it, so I'm going to talk about it now and then just finish the final adjustment we're going to make to this, right? So this is the selection sort code that we have worked to templatize into a template function, and now it will sort vectors of unknown type. And the change we had just made, the one that's highlighted here in blue, was rather than directly taking v sub j and v sub min index and comparing them using a less than, is that we're using a callback function. This callback function's the parameter CMP, or compare there, takes two parameters that are of the client's type, returns an int, which is their ordering, 0, negative, or positive, and that instead of making a direct expression involving less than, we're invoking the client's callback on the two things that we need to compare and saying if that result is less than 0, so v sub j precedes the v of the min index, so it's actually smaller than the min element we've seen so far, then we update our min index to record j as the place we've seen it, and then it goes to the rest of the code normally, swapping that small thing out to the front and then going back around for multiple iterations to keep doing that. With this change, right, we have now kind of generalized this fully in a way that you can sort vectors of strings or vectors of coordinate structures or students or vectors of sets of things, as long as the client supplies the appropriate comparison function that explains how do you want those things ordered, which ones go in the front, which ones go in the back, is up to the client to say by giving us that callback. And so a client could use this, for example, to sort coordinates, something that has kind of an x and a y field, by deciding that, well, if first on the base of the x-coordinate, if the first one's x-coordinate precedes the other, then it's considered less than. You have to make up an ordering, right, that represents what you want. In this case, I'm going to say that, well, first sort on the x dimension, moving smaller values of x to the front. And where they are tied in the x dimension, then use the y to break ties here, looking at the y fields, if it has gotten through those first cases of x compared between C1 and C2. And if all of those things have kind of not been true, then we know that at this point x and y are exactly equal, and so we have two elements that are the same. And so given a vector of chord, right, I would invoke sort, passing that vector, and then the matching comparison function that lets the sorting routine know how to take two chords and decide which goes in front. Yeah, sure.
Where we use the type name template, is type name a special word?
It is. So the type name is a C++ keyword that says this template depends on a type name. There are actually other things you can templatize on. We won't see that this quarter, but I'll just kind of leave it as a thing that there are other things that you may actually have as kind of parameters to the pattern that you're using. The one we're going to see is when we are actually using a type as a placeholder. And so type name means there is a type in the body that follows, right? There will be usage of the keyword of our chosen word type as a placeholder for something that is supposed to be a type name. The other word there, the TYPE, right, that was our choice. That could be T or E or F or my type or whatever it is I wanted. That was just a name we got to pick. There's my chord compare. And the last thing I'm going to do with this is just make it a little bit more convenient that given the form I have right now, it says that there really are always going to be two parameters. You're going to give it a vector and you're going to give it a comparison callback function. Before I went to all this trouble to make it have a comparison function, it used to actually just work by default for things like ints and doubles and strings that actually already operated correctly with less than. And so what I'm going to do is having made it generalizable, I'm also going to go back and add in a default behavior which says, well, if you don't care otherwise and the default less than would work for you, then let's go ahead and use that unless otherwise indicated, so that kind of we got back the original behavior we wanted, which is you can just say sort a vector of numbers and have it do the right thing without having to go to trouble of building a compare int function to pass to it. So what we will do is we have an operator compare. I'll show you what it looks like here. That there is another header file in the 106B collection called cmpfunction.h. It looks like this. It is a template function itself. It's called operator compare that takes two type things, and then it uses equals, equals, and less than to decide whether to return a 0, a -1, or a 1. And so operator compare will only work when instantiated for types for which the built-in equals, equals, and less than are defined and make sense. That includes all the the regular primitive types, int, double, and whatnot, and also includes the string class, and then potentially other classes, right, that you may know of that actually have behaviors that have implemented those operators. It will not work on things like structs or vectors or other things that don't have the behavior for this, and it's not intended for those. It's kind of just a pattern from which you can build the comparison function needed for the form by sort. And so then I changed the prototype here of sort. It takes a vector of that type, it takes a comparison function that takes these two things, and then I said a default argument for that is to use operator compare. And so when somebody invokes sort, not passing the second argument, then what that will cause the code to do is say, okay, well, they didn't pass it. We need to use the default expression over here, and then operator compare will be instantiated for whatever the type is. So if it was string, then it will build an operator compare that operates on strings. If it were int or double or anything that has a meaningful way to apply the built-in operators, it will use that. If I still called sort, in this case passing, let's say, vector of cores, so if I went back to this picture, and I forgot this argument, right, I will get a compiler error. And the compiler error will come from trying to instantiate an operator compare that works on chord, where it will get to that line about equals, equals, and less than, and say, you're comparing two structure types, and that doesn't make sense to me. So in this case, the client has the choice of specifying it when they intend to control that behavior, or they need to control that behavior. They can also leave it off in the cases where that default of the operator compare will do what they wanted anyway. So I have an example here at the end that says if I wanted to sort an array of numbers, I won't need to pass a second argument in the case where I just want them sorted in ordinary increasing order. If I wanted, for example, to sort in inverted order, I want the largest value to come to the front, that I don't need to run a new sorting routine that then goes and looks for the max and pulls it to the front. I just need to trick selection sort here into believing that the larger numbers go in front of the smaller ones. So I basically wrote an inverted compare function that if A is less than B, it returns 1, which basically says, well, B goes before A in the ordering I want, which is the larger ones should precede it in the output. And similarly for the other case, and then returning 0 when they're the same. So this gives us control when we want it, in the case of the primitives, as well as control when we need it for those types for which the built-ins don't have defined behavior for it. So this makes this like the end-all, be-all sorting template. Everything you could want in one package. You will be writing something that looks just like this for the second part of the assignment this week. And then what will differ is, well, how does it do its work? What strategies is it using to get things in order? But the overall design of it is to build this general purpose, could be used for anything, has a client callback option, also has a default used that makes for very nice convenience as a client. Any questions about that? Is your life or what?
I have a question on the line right below. It says right below the void line. So what does that do?
So the line that's underneath this one here. So this is the one that says the second parameter. So the first parameter is a vector of type by reference. The second says the second parameter is a comparison function that takes two type arguments and returns an int. And the default assignment to that parameter, if you have not specified it, will be to use operator compare. So it's got a lot of things mashed in there. The syntax for the passing a function as a parameter is a little bit goopy in C++. It kind of includes what looks like a full prototype, because that describes for the compiler, well, what kind of functions are they? And they have to have this parameters in this order, this return type. So we actually kind of have to give this full information about what the shape of such a function is so that it can match it. It can't just take any function, right? I can't pass it getLine or, convert to lowercase, and like not just any function is good. I need to give a description of what kind of functions are right, and those are the kind of functions that take two type arguments and return an int, and that's what we're helping the compiler out there with all that syntax.
Wait, and how will it know if you have a comparison function based on that call?
So this isn't the call, right? This is the function I define.
Okay.
So when I make a call to sort, so if I look at this one, it's all a matter of do I pass one argument or two? It's just a default argument. If I don't specify it, then it will use the default value, just like any of the default argument things we know about, like find on a string, which if you don't say, it will start at position 0 doing a search. If you do specify that it uses your index instead. All right. Let me move on. So in your 106A class, right, you did a lot of things in the genre of object-oriented programming. This class is not really an object-oriented programming class. It's a class that's in many ways very procedural, but we use a lot of objects. And what I want to do just for a minute here is just kind of reiterate the advantages of using objects in your code, what it is that they provide in terms of structuring and engineering and working to a solution. And then we're going to go on and start talking about, well, we've used a lot of objects. What does the other side look like? What is it like to implement an object starting from scratch? What pieces need to be done and how does that work? And so the idea of just object-oriented programming is actually, it's a relatively new concept in computer programming, right? It only dates back to the 80s. And the realization, right, that programs at that time, right, you're operating on a lot of data. You're moving around employees, or you're managing this calendar, which has these events that are at certain times. And that you had a lot of operations that were obviously intended to work on that data, like move this event to another time, or calculate whether this time precedes another or conflicts with this. And that operations, though, the functions that manipulated that data and the data itself were not really very tightly coupled in the kind of past. And the idea of object-oriented programming is to really couple those things together, is to say that if you have a data type, like a time or a stack or a vector, that the operations that manipulate a vector are best made as part of the package of vector itself. That rather than there being a print vector function that operates somewhere else, having vector have a print method. Putting something onto a stack or asking it for its size is really an operation that should be owned by the stack, that a stack variable should be able to respond to requests to do things on your behalf through messaging. And so this idea has become kind of permeated the language design in the last decade or so, to where pretty much every modern language has some facility for object orientation. Even older languages that didn't in 4 have been updated and brought forward, right, to Visual Basic, right? Basic, which has been around for half a century, is now objectified, right, in its latest versions. So the idea that they leverage to the real world is actually an important part of the advantage, that when you talk about a time or a stack or an event or a message, if you're doing a mail program, those things have real world meaning. And so the idea of what they do and how they act actually there's a lot of leverage of what you already know to be true about those things in the real world. The notion of kind of dividing it up and saying, here's this abstraction of what a stack is. So we've used stacks all along, push and pop, right? Push and pop. What does it really do? How does it really manage stuff? Where's the memory coming from? What internal structures is not actually something we have to worry about. We're using it abstractly. We're saying it's a stack. It has push and pop behaviors. All the other details of how it works are not something we have to worry about. So it lets us focus on solving other problems, more interesting problems than the kind of things that happen behind the scenes. They're also very tightly encapsulated. So we're not mucking with the stack. It's actually acting for us as a black box it's kind of like one of those microwaves where it says on the back, if you take this panel off, right, you void your warranty. Like, I don't know how my microwave works. I never take that panel off. I hit the buttons on the front. Food gets hot. I'm very happy. And then things that happen in the large, as you get to building larger and larger projects, right, the idea that multiple engineers are working together and designing on different time frames, that having things divided into these very strongly encapsulated bundles makes it possible to design and test independently of your partners and then join back together and have a much better eventual result than if everybody's trying to write all the same code in the same places on top of each other without real discipline to it. Nice packaging for reviews. Something we've been seeing a lot of, right, is that things that lexicon or stack or queue we've used in a lot of different ways, sort of a multi-purpose object. Let me tell you about who does what in here and what new roles we're moving into, right? We have done a lot of client use of objects. So a program like the maze program or the random writer program is some code file containing actual code.cpp. It messages to objects. It creates objects. It asks them to do things on its behalf. Every class that it is using, it includes the class.h, so stack.h or queue.h or vector.h, based on what it needs. And so this is the only role we have played so far. We've been client. We've used them. We don't know anything about these other two things that need to get done. In the middle, between the client and the implementation here, is something called the interface. We have looked at these header files like stack.h and queue.h, and that tells you about what the class provides, what abstraction it is, what its member functions are, what their names are, what their parameters are, what the correct usage of it is. And so this serves as information to the client about what you can do and what you can't do, what's legal, what's available. And it doesn't contain any, though, inner information about, well, how does it really work? What does it do behind the scenes? You know, what kind of things can you expect other than kind of what's the correct behavior to expect from it? What we're moving into, right, is looking at this role and this role over here on the right, which is what does that implementation side work look like? So if we have described what lexicon is, it's a word list where you can check for the existence of a word or the match of a prefix. And it's our job now to implement that. It's like, well, what are we going to do? Now, this is where we get down and dirty, right? Now it's not about, you know, the pretty abstraction. It's about making it work well, making it work efficiently, using appropriate data structures, making it robust, making it handle kind of all kinds of things you throw at it. So, for example, the vector class. If you ask it to get something that's off the index, right, it's going to tell you about it, right? So taking care to make sure the thing just works in all situations, is very bulletproof, is very sturdy, is very informative, right? And well designed, sort of clean, easy to use, does the right things, has the right functionality, isn't missing anything, and that implements it well. And so in this file, the stack.cpp or the scanner.cpp, right, we have all the code for the member functions. So we make the things really happen. We include the class interface too, because the interface actually is used by both people. The interface on this side tells the client what's there, what you can do. The interface tells the implementer what needs to work. Right? You have offered up a method called contains prefix or contains word, then it's the implementation's job to make that thing do the right thing and return the right answer. So let's look at a simple class. The class I'm going to talk you through is one of creating a time, sort of a moment in time, 2:15, that potentially, right, you might be using, let's say, in a calendaring program to decide what events you have scheduled for a particular day. You'd like to say, well, it's at this time, and then the idea of time and things that manipulate time, it actually makes a very good object. It has a very real-world analog about what a time is, and there's a lot of behavior that seems to go with a time. So in the .h file, which is the interface for this, will be the listing of the class. So the outer structures for this are class time, and then open curly brace, close curly brace, and then a closing semicolon. This kind of models the same syntax that C++ uses for structs, where you say struct something, and then you have these fields, and you also have this closing semicolon. That semicolon, right, is not present in Java, and it's a pretty easy thing to leave off and then get a lot of compiler error messages that are a little bit goofy from it. So one thing you'll just want to register as something to be attentive to. What the interface declares, so this is separate in Java, not separate in Java, I'm saying in C++ it is there actually really is a file that says what the class provides, and there's another class that says how it works. In Java, those were kind of one and the same, that the definition of the class and the kind of interface of it were not separated and maintained separately. There are advantages to this and disadvantages. It means there's two separate files. It means that what you give to somebody who's using your code doesn't contain any of the things you don't want them to see, how it works and how it's internally configured. But it also means that you have to keep the two in sync, just the same way any kind of separate prototyping does, is if you change the name in one place, you have to change it in both places to kind of make sure that they're always in match. So the two main things that get declared within the class declaration or its interface are the data members, so the fields that are a part of a particular time object. And these are declared like ordinary variables, int, hour, minute. They could be variables of other types, string, vector, and things like that. As long as anything I'm using, I would have to pound include at the top. And in this case, I have introduced them under a private section. So unlike Java, where every single field has its own private or public modifier, in C++ you actually introduce a section with private colon, and then everything from there on down is private until it sees something that changes that back to public. So typically, right, you'll have one big public section, one smaller private section. They could be in the other order. Either way, I typically use this form where the public things sit at the top and the private beneath. The other things that get declared as part of your interface is what member functions are available. What are the operations that you can manipulate a time with? And so maybe right here I have something that allows you to change the hour or get the current hour from a time or move it forward by some amount of hours and minutes. I want to push back that meeting by an hour and 50 minutes. I could call shift by 1:45 to do that. Something that converts time into a string format, maybe suitable for printing or using in a display, is a two-string member function I could add, and the time class is part of its public interface. And so the whole list of what I have here, and so kind of as a rough rule, right, most of your functions will end up public because they're operations you're offering. Your data is almost always private. You don't want to make that accessible outside of the class. And then occasionally, right, there are reasons actually to have some member functions that are private. They're used internally as helpers, and they're part of the strategy, but they're not something you want a client to be able to directly call. So you actually keep them in the private section to indicate they're not part of the interface a client needs to know about. You've seen a little time. Any questions about what it looks like there? So the time object I have declared here has two data members, an integer hour and an integer minute. The mechanics of how this works is that the object is basically about the same size as the comparable struct. So it has fields for hour and minute. It doesn't actually have a bunch of storage for the member functions. Since those are shared across all times, there's no reason to have every time carry around a duplicate of that. So what it really carries is its own fields, the data members that were declared in the class. And so when I say time t, what I'm getting space for, it looks a lot like a struct, something that has an hour and a minute field. By default, the initialization of those fields is as it would be if they were just declared on the stack. So if I said int hour, int minute, I would just get junk contents. So it doesn't set them to 0 or do anything clever on our behalf with these primitive types. It just lets them stay uninitialized. So we'll see about how to fix that in a minute, but just to know. And that when we talk about time objects, right, every single time object has its own hour and minute. So this time is 2:15, this time is 7 p.m., and the numbers that they are storing and maintaining, right, are different for their hour and minute. So it's kind of like across all the different time objects, there is individual hour and minute fields associated with each particular time. So it all kind of seemed to make sense back to the 106A days where you did a lot of this. So if you have a time object, and you've already seen this, but just to mention that, yeah, you access its member functions and its fields using dot notation. If you happen to have a pointer, you can use the arrow, which combines the star and the dot. Calling set hour, calling get hour, trying to access a field, that both the member function use and the field use is dependent on the feature that I'm trying to access being declared public. If it was in a private section, and if you don't specify, if you forget to put any of the access specifiers on it, by default they were all private. And so my attempt to access any of these things that were private will result in a compiler error. So it won't let me get past that kind of mistake. The object being message, we call that the receiver, and we've talked about that before. T being the receiver to the set hour, and the assumption being that what I'm trying to do is tell this time object, right, to set the hour it is to 3, overriding whatever value was there before. Now, what does it look like on the other side? If you are the implementer of time, what kind of things do you have to do to make time behave the way you said it would? You have a file, time.cpp. That's the class implementation file for it. The first thing it will always do is include the class file that it's working on. That's because if I start defining the features of class, I need to know what they are so the compiler can check and make sure that I'm telling the truth, right? That the functions that I'm trying to implement and their parameters and the data members I'm trying to use match the description I earlier gave about what time was. So both the client needs to see it to use it, the implementer needs to see it to implement the right things that have the right names or the right prototypes. This is where all the code for the member function goes, is in this file. And there's a little bit of a syntax that you'll need to know about this, which is when I'm ready to implement the set hour member function, that the name that it goes by, its full name, its kind of real name, is time : set hour. That everything that was defined in the time class is considered to be within this scope, and C++ is not the word for that, is the scope time, and that the way to access something from within a scope is to use the name of the scope, : and then the thing you wanted to get out, you were trying to define, trying to use, and whatnot. So when we're defining all these member functions, we're saying it's the times set hour member function that I'm writing, not just a function called set hour. If I leave this off, I have a function that says void set hour int new value. What the compiler thinks I'm writing there is just an ordinary global function. It thinks there's a global function whose name is set hour. It takes one parameter, which is int, and it returns a void. It doesn't think it has anything to do with the time class. And the next thing it will notice is in here, when I'm trying to access features that are relative to time, it will start giving me compiler errors. It'll say hour, where did hour come from? You know, I know about new value, it's a parameter, but hour just came out of nowhere. That looks completely undeclared to me. Something must be wrong. So if that's a mistake you will certainly make at least once, and we'll want to commit to being attentive about. It's like it is the time set hour, it is the times to string, and that is distinguished from other functions of that same name. That actually is kind of a neat, though, feature of the fact that works that way. For example, there's the member function size shows up on a lot of our classes, on vector, on stack, on string, on map. That the idea that all of those things can be called size is actually really handy, because who wants to remember that one of them's length and one of them's size and one of them's num entries and one of them's depth and one of them's length or something. That having them all be size means that you have this one name you use when you want to get the information about how big a collection is, and the fact that the compiler can keep them all straight is based on this scoping mechanism. You know that there's a vector size which is different than stack size, which is different than map size, and it doesn't confuse them up because it has this scoping to keep it all straight. So when we're writing the implementation of our member functions, there's a couple things, right, that we need to know about how to make them work the way they're supposed to. So in the time member function like shift by, that if we just refer to the field hour or minute, one of the data members of a time object, it is assumed that the hour or minute we're talking about is of the receiver. So shift by is never called without a receiver. There's no mechanism that lets you just call shift by without something in front of it. So shift by got called. There's some time object somewhere where it says t.shift by an hour and 15 minutes that moves the t time forward by that amount of hour and minute change. So in the context of shift by, you can count on that hour and minute refer to the fields of a receiving time object that currently has some value in the hour and minute that we're changing by some delta to move it forward. So any reference to the hour and minute fields with no other qualifying marks means my hour, my minute, the one that got the message. In the body of the member function, we also, so we can directly access these fields, we can also make further calls to other member functions. If there is a set hour and a set minute setter that are available on the time object, then we can say set hour, hour plus d, hour, the minute plus d minute, and then that will go through our own setter to update the hour and minute field to the new values. So this is a case where you're seeing a call to a member function without an explicit receiver. And in this case, the receiver is assumed to be the same receiver who originally got the shift by message. So this really isn't dropping the receiver or losing it. It's actually just assuming that without any other explicit receiver, that it means me. So the time object that was asked to shift tells itself to change the hour and change the minute. We're going to talk a little bit about why that might be an important strategy relative to the alternative here, but just to know that mechanically they both work. And then the last thing I'll note is this secret variable, this idea that it knows who the receiver is, and that it's actually using it as part of the access for the hour and the minute and the caller. That there actually is a way to explicitly access that syntax if you want to know. There is a special variable called this that is only valid within the member function of some class, any class. This is a pointer to the receiver object. So this, in a time member function, is a time pointer. In a stack, it would be a stack pointer, and so on. And I can use the longhand form of this arrow hour to mean take the time, this, dereference it to get to the time object and access its hour field. Similarly, the this arrow set minute is doing the dereference and then sending itself the member function. This is equivalent, right, to dropping that entirely. So you will rarely see a C++ programmer actually use this longhand form, but it is the mechanism behind it. You can see explicitly in situations where you might want to be very clear about it. Sometimes you'll use that, for example, when you have two time objects and you're trying to compare them. You want to be distinguishing the parameter from this. You might explicitly say this hour. If this hour equals others hour, you might want to make that clear which one you're talking about rather than dropping it in that situation. Any questions about a little bit of mechanics? So I said that I would talk a little bit about, well, why might you want to have your member functions just make calls to other member functions rather than directly modify those fields? And one of the advantages, right, of that object-oriented programming is that you can actually really be very tightly managing the object state and trying to make sure that the object never gets inconsistent. For example, if you're a stack, you want to be sure that if you think the depth of the stack is 10, that there are 10 valid elements. You never want to get in a situation where somehow you think they're 8, but really they're 10, or vice versa, that it's your job to make sure that it makes sense. In the case of time, there's actually kind of a lot of invalid or illegal time values that you could imagine sneaking into your system, where suddenly you have the time, 55, negative 14, right? You want to be sure that the hour and minute really makes sense for what you know to be the domain of valid times. By having the instance variables be private, the data members, nobody can muck with them other than you and the implementation. And so if you actually are very disciplined about making sure they can't ever get wrong, that no matter what operations you offer, shifting it forward, shifting it back, resetting it to new values, you make sure that there's no way a bad value can creep in. And probably the easiest way to do that is to build a gatekeeper, is to have there be one central point where you change hour and everything goes through that one central point, and that central point is designed to make sure that nothing can sneak past it. So if somebody tries to change the hour to something that's not between 1 and 12, you can just decide to bound it. This may not be the right thing to do. Maybe I should raise an error, but at the very least, right, I need to do something if they give me negative 14 or 82. And so right now it chooses to just say, well, I'll just bring it to the closest value that's in range. An error would be a completely valid alternative. Similarly, something about the minute. If they give me a minute that's not something between 0 and 59, that doesn't make sense. And so I just modded it, just to take the lower order part of it. If these are the only places, let's say, imagine in all of the time class where I ever assign to hour and minute, and everywhere else where I want to change it, I say, well, here, change it by this much and stick it through. Here's the value I'd like to set it to. Let me ask set hour to do it on my behalf, that if I've made some error in the calculation or I've been asked to do something kind of ridiculous, that it will cause the right eventual assignment to get made. And so that's why I say, what's this advantage? Why would we want to do this? It's about control, right? Kind of centralizing the access and the robustness of your interface to say, well, here's the one place where I ever change it. Let's make sure everything goes through that same interface, and that way there's no way you can sneak through some back door a bad value in. So a couple other things you need to know about class mechanics. There are a few special member functions. One is the constructor. So the constructor is it's just automatically tied in with allocation, that when you allocate an object, either with new or on the stack, the constructor is automatically invoked as part of that process. And so that gives you your opportunity, if you define a constructor, to set up your data members the way you want. If you don't specify a constructor, you get the default constructor. The default constructor takes no arguments and basically does nothing to your arguments. So it leaves them uninitialized. So for most things, that's not going to be appropriate. It's probably the first thing you want to do when you make a class is to write a constructor that sets yourself into a known good state. It has a special prototype. It has to have exactly the same name as the class. It has no return type, not void, not anything. So it looks a little strange when you first see it. And then it can have parameters if you need them. It also can be overloaded if you want more than one constructor. You can have multiple of them. So if I were to add one to my time class, I put in a function, you notice, has no return type, right? So the first thing you're seeing is the name of the constructor, which has to exactly match the case and name of the class itself, time, and I'm, in this case, choosing to make a constructor that takes 2 integer arguments, the starting hour and minute that I want. In the CPP, right, the implementation of the constructor, time within the scope of the time class, time, : time, again, no return type here, taking the hour and minute and setting it. I can actually make calls to my member functions, and given my earlier little speech about this, it seems like it would be even better, for example, to be calling set hour of HR and set minute of min, to just make sure that even if they give me initial values that are total garbage, right, that I don't let the time start off with some negative 45, 100 kind of state that doesn't make sense. Once this constructor is in place, right, then the calls to create a time will show 2 arguments are required to construct a time that's to specify the hour and minute. It's no longer optional. Whereas prior to having a constructor, there was a default constructor. The default constructor took no arguments. Once you declare any constructors, the compiler stops giving you anything for free. And so if you want both a default constructor and another several argument constructor, you'll just make several of them. You could have a time here that just says time, open paren, close paren, and then have a time, : time, open paren, close paren, that set the hour and minute to some default, 12 o'clock or whatever you wanted. You can have as many constructors as you need. But typically, I would say most classes have one or two. There's not that many starting configurations you need to support typically. So something that's new to you, if you're coming from the Java world, is the idea that there's a corresponding parallel function that is tied into deallocation. That when an object is going away, the two times when an object is going away, one is when it's leaving scope for a stack allocated object. So if you have time t declared in some for loop, and when you exit the for loop, it automatically deallocates that object or destructs it, it can be said. If you have newed that object, new timeout in the heap, that when you delete that time object as part of the deallocation of memory, it will destruct it. So what it does is it calls the destructor when that happens. The destructor is your hook for I need to clean up when this object is going away. It has the same name as the class, but prefixed with a tilde. So tilde time is the destructor for the time class. It can never have any parameters, and it never has any return type. So time is the constructor name, tilde time is the destructor's name. You don't always need a destructor. It's actually a little bit more unusual with some simple classes that what you would need it for is if there were something that you did as part of constructing or building the object that you needed to clean up. And the most common need for that is you have dynamically allocated some members. So you have an object that holds onto a linked list and has just a pointer to the head node and a bunch of cells that follow it, that when you were destructing, you would want to go trace that linked list down and delete all those cells if you were going to clean up after yourself. If you don't do that, you don't have a destructor, right, then the pointers just get orphaned and all that memory is just hanging out there clouding your heap. Sometimes there are things about opening files, like maybe you have a bunch of buffered output that you want to be sure got committed to disk, or a network connection you want to close, or something like that. So things that are open that you need to release. So typically it's like resources that you need to clean up around that goes in the destructor. For the time class, there'd be no need, right? We have just simple integer variables. There's nothing special about them, so we don't actually need to go build a destructor. But some of the classes we'll see later will have a reason for that. So this idea of object design is sort of one of the more important points to think about when you're setting up and building an object, right? Is that it's your responsibility to make an object that kind of does what it says it's going to do and tries its best to be robust in the face of all situations. Even in this case that maybe the client uses it incorrectly. That the point of the sort of programming is it's not to think that we're programming among enemies or we're malicious, but the idea is people make mistakes, right? People accidentally have the time and they change it to something that doesn't make sense, or they do the calculation incorrectly, or they access off the end of the vector. That having the response to that by your object be to crash, or to just produce incorrect information, or to return an erroneous result is really not, doing the best you can. And so part of your goal in designing this object is just to build something that really, is a lovely work of art that does exactly what you want and catches all the mistakes, and even things that are really just the client's fault, right? Asking you to do irrational things are handled gracefully. And so part of that is really taking kind of a big picture view of all the operations on the class and making sure that you have published the operations that are appropriate, right? That they respond to all forms of input gracefully, and that they kind of manage the object state as it moves through the different operations in a way that's consistent. And so part of that is thinking about, well, who accesses the data where, and making sure that those accesses are really understood and controlled. Never having any public data members. Once you have a public data member, all bets are off. If hour and minute are public, anybody, anywhere, anytime can just reach right in and change into whatever they want. All guarantees are lost. So you would never want to do that, right? You are exposing part of your internals, right, for everyone to see. It's like having the door in the back of the microwave. You just open it up and you can start like rewiring. It's like that's not going to end well. You correctly initialize all your members in your constructor, and then you consider where and when to allow access to directly modify those things, if like through a setter, if it's needed and if it is properly constrained. The other thing that's an important part of kind of designing the interface is making sure that the object kind of is fully formed, that it does all the things you'd like it to do, and kind of simplifies the client's use of it, as opposed to kind of going half the job and leaving them to have to do a bunch of other things. It has a complete kind of coherent set of applications. So like if you needed to print a time, that one way you could supply that is you could say, well, you can get the hour, you can get the minute, and you can convert them to string, and you can put a colon in the middle of them, and then you can print it. Why bother me about it? Like, you want to print a time, that's your business. On the other hand, right, printing seems like a pretty fundamental operation that would just be nice for time to support. Maybe it supports it by having just a print method. Maybe it supports it by giving you a string form, like toString, where it does those calculations, converts it and gives it back to you. And then you can decide to just output it as a string. But having that be a part of the class really makes the client's job just easier. They're likely to need something like that. Why make everybody who uses your time class have to reproduce this functionality that really feels like something the time class itself should support? And so when you think about your set of operations, you have some list you might need in the near future. You're also trying to think a little bit more big picture about, well, in all the situations you use times, what kind of operations come out as being useful? While I'm implementing time, why don't I just kind of build, the full-fledged version that has the functionality for the things that I imagine to be likely to be needed? So comparing, right, 2 times, is this one before this one? Are they equal, right? Moving them around, just kind of giving you the whole package. So there's a little thought about one of the advantages, right, of the object design or object encapsulation means that you have described what time does. You say it allows you to set the hour. You have described that it'll compare them to see if one's less than another. You have a toString or a shift by. But you have made no guarantees to them about what you really do, how you really internally work it. The time interface might describe things like in terms of hour and minute. Oh, it's an hour and a minute in time, and you can shift it by hours and minutes. You can ask me for the hour and the minute. But internally, there's no rule that says, because our interface says hour and minute, that we have to have fields called hour and fields called minute. That, in fact, manipulating it, right, as hour and minute is messy. And if you throw in AM, PM, it's even worse. That all the things, like, for example, decide if one time is less than another, it's like, well, if this one's AM and that one's PM, then it's less than, right? And if they're both AM or PM, right, then we start looking at the hour. And if the hour's the same, we start looking at the minute. Like, it just doesn't, it gets goopy, right? We can make it work, but why do it if we don't have to? So if we just instead pick a different representation, it's our internals. Nobody needs to know what we're doing. It's like, I don't want to keep track of hour and minute. Hour and minute is some other artificial sort of human representation. Computers are really good at much more simple things like, well, what if I just said, look, every day, every minute within the day is assigned a number. 0 is midnight, right? And then, 720, right, is noon. And just, well, whatever, you say minutes since midnight. 2 minutes since midnight is, 12:02, right? 10 minutes is 12:10. 60 minutes is 1 a.m. Right? I just mark everything down there. And then it turns out, right, a lot of my operations become really easy. I want to see if this time is less than the other. It's like, okay, just, compare their 2 minutes since midnight. I want to move a time 60 minutes forward. Well, I just add 60 minutes to whatever number I have. You can do the wrap around really easily. So like if you were close to the end of the day, you're at 11:30 and you add an hour, right? It's very easy to just use mod to wrap you back around to the 12:30. That if you're doing it with hours and minutes and AM, PM, all those things are very ugly. So the thing is, we can still describe our interface as hours and minutes because that's how clients want to see it. But internally, we get to make all the decisions we want, and we might as well make the ones that make our lives easier, make it easier to get the code right. It's actually, it takes less time to do the operations, right? It will run more efficiently. It uses less space, in fact. And it just made everything easier from our point of view. And it turns out we can still have operators like set hour and set minute and get minute, right? They just internally kind of convert to the internal representation, but they provide an interface, right, that seems appropriate for the client. It doesn't mean it has to match what we do inside. So that's actually kind of a really neat thing to keep in mind, right, is that's part of what we've bought, is that they don't actually have any guarantee about how we implemented it, and we're not going to tell them. So I will kind of leave you with this thought about abstraction, because that is sort of a key advantage of working this way, right, is there really is a wall between the client and the implementer that is an important part of it feels like a restriction, it feels like a jail, it feels like a prison if you think about it that way, but in fact it's liberating. It means we're not in each other's hair, we're not dependent on each other in any meaningful way. We have this little tiny conduit, that chink in the wall we call the interface, that describes what things we both can depend on, but then everything else is at the liberty of the person, who's on their side of the wall to do what they want, without regard to what the other person's expectations are. So we'll think about that in terms of, let's say, lexicon and scanner and vector and all these kind of neat things on Friday to kind of dig around the backside and see what we've been missing out on. I will see you guys then.